We're going to continue to build on covalent compounds, or at least situations like polyatomic ions in which you have covalent bonds. And we're going to talk about shape. So this concept, I think it's pretty cool, valence shell electron pair repulsion theory, all that is talking about shape around an atom. Okay, so you have your Lewis structure. You know how many, for instance, sigma bonds are associated with an atom. You know how many pi bonds, you know how many lone pair electrons. Then you can get shape around an atom. I like valence shell electron pair repulsion theory because it can kind of be summed up into this, I call it VSEPR, but it's not really VSEPR, but VSEPR, VSEPR theory. Okay, we've talked about valence shell electrons, right? You know the number of valence electrons or the valence shell electron of an atom by looking at its group number. Okay, we talked about how those valence electrons then go into a pot of valence electrons if that atom is bonded to another atom. We talked about this idea of pairs. We've talked about a lot of pairs. Remember, anytime you see a dash, that's a pair. Anytime you see a double bond, that's two pair. Anytime you see a triple bond, that's three pair. There's a pair, a lone pair of electrons. And this idea of repulsion is kind of cool because actually if we have an atom A, I'll just draw this as like the atom, these things, these sigma bonds, lone pair electrons, and pi bonds are going to repulse or scatter as far apart as they can from the atom. Okay, so that's the repulsion part of it. Valence shell electron pair repulsion theory. It gives, again, shape around an atom. Okay, so it's pretty exciting. I've got some pictures coming up here to kind of show you the valence shell electron pair repulsion theory in action. So things we've already talked about, it's kind of nice, just kind of remember how this works. Sigma bonds, remember, are your primary bonds. They are the first to arrive. Okay. So sigma bonds, we said that those electrons are located, sigma bonds and lone pair electrons will scatter as far apart as they can from each other. And it's going to be easier to show you here in a minute, but like if this is my atom, they're going to get as far apart as possible. Okay, and it's kind of an electro static thing they want because they're electrons, okay? This is where I thought I was a minute ago. We said that actually the sigma bond, the primary bond, lies between the two nuclei, and that the pi bonds, electrons, actually lie outside. So if you're thinking of a hot dog sandwich, the sigma bond is the hot dog, and the pi bond is the bun, okay? So one of the things when it comes to, I'm going to try to convince you of this, but when it comes to pi bonds, okay, pi bonds do not give shape. Pi bonds, okay, equals no shape because they are basically just going to kind of hover around the sigma bond. Okay, so what else do we need? So as I talk about shape, I'm going to really limit it to shape around an atom, okay? Three-dimensional shape around an atom. Now we could go atom by atom by atom and then kind of build up to the molecule, but I just want to concentrate just on around an atom. Now that shape around an atom is called structural geometry. Notice, and I'm not even going to put it up here, there's molecular geometry. That's the geometry of the entire molecule. Structural geometry is simple, just an atom, so don't make it more complicated. A synonym for structural geometry of an atom is electron pair geometry. I'm not going to go into it too much, but I think it's pretty amazing. Well, I have to go into a little bit, but when an atom takes its atomic orbitals and prepares to overlap with the atomic orbitals of another atom, oftentimes that atom will hybridize its atomic orbitals to extend hybridized orbitals to go ahead and participate in either sigma bonds or lone pair electrons. And we're going to talk about 3 different hybridization situations where an atom hybridizes its orbitals. Okay, so keep all that in mind.